Hello, YouTube. So this is the final, not really lab, but the final project, the final boss of this course, Tuesday. This is only 3 pages, gradient descent algorithm. So Nikolai will answer any questions as they come in the chat. Let's see. I'll get my drawing pad as well so I can actually annotate this thing without using a mouse. Bad. 10 seconds to set this up. Should do this before the recording, but there we go. Okay, I think there's a useful visualization in the slides as well. I'll show that kind of after we get into this. So it's gradient descent algorithm. I'll kind of like draw out like what we're doing here. So first of all, Professor Lee went over this yesterday in lecture. So if you haven't already, check out the recorded lecture, lecture 27. The timestamp is I think like 51 minutes and 30 seconds. So then he goes over like the optimization project. So check that out. Now, as for like what you guys will be doing, it goes like this. Like you have, like imagine like a hill or like a valley. We're going to use MATLAB to do this series of steps. Pick a point. We're a hiker. Okay, we're standing right here. Now, there's a couple things I could do. I could apply something called gradient ascent, which is I want to go up the mountain. Or I could apply something called gradient descent. Oh, this is ascent. This is descent. These are not very high-tech visuals, but it highlights an important point. So how do we tell MATLAB to do this? So like the idea behind this, by the way, is to locate where these peaks and valleys are. We're going to have like this 6 by 6 grid, right? This is like in the XY plane. This is X, this is Y. And then this like fabric or whatever, it's going to have peaks, it's going to have valleys, it's going to have like saddle points in between. Now we want to tell MATLAB, hey, find where these peaks, find where these valleys are. Now, a 5-year-old can do that, but MATLAB's not a 5-year-old human child. It's MATLAB. So we need to tell it, we need to give it an algorithm to kind of say, hey, if we're standing here, how do we like iteratively find where these peaks are? Well, one way to do it is gradient descent and / gradient ascent. And what this is this. You have something like over here and over here, gradient ascent, gradient descent. So what do all these symbols mean? So I'm gonna kind of take this over here. We have xn plus 1. We're starting at x. No, hold on. That's an equal sign. This is where we are. Well, no, I'm going to write you are here. This is where the hiker is standing at this current moment. The hiker wants to go over here, the next position. They're going to walk from x to x sub n to xn plus 1. Well, how are they going to walk there? Like, where is this xn plus 1 you speak of? Well, if in this ascent case, it's going to be some point that's like further up the mountain. Now, further up in MATLAB speak is like we follow the gradient. And what the gradient is it's an arrow. It points up the mountain. Now, the reason why what gradient descent subtracts this, by the way, so here's the gradient. If we subtract the gradient, if we like go in the opposite direction as the direction of greatest increase, then we're going to go down the mountain. That's what this minus sign, that's what this plus sign means. So you are here. We want to, let's go up the mountain, shall we? Let's go up the mountain and we're going to add gradient of f, x sub n. This means, like, this is what it looks like over here. Partial derivatives in the x and the y direction. And what's this gamma over here? Well, gamma is this learning rate. It's like, how fast are we going to run up this mountain? Like, are we walking? Is gamma very, very small? Or are we like running at a very, very fast speed? So that's the learning rate. So learn rate. it's like the step size when we were doing, I forget which problem from my previous lab. So gradient, grad, and go here. I guess like run speed. Conceptual basis for what we're trying to do here. Go up the mountain, go down the mountain. Okay, so here's the idea behind how to code this thing, which you guys probably are more interested in. So first of all, let's see, I have some notes on this. I wonder if I should just share those. Let me check if these are good enough to show. Okay, yeah. Well, let's do this. How about this? I'm going to stop sharing this for a moment. I'm going to take a screenshot of this, but I'm going to stop sharing in say 10 seconds, and then I'll pull up the notes that I have for like how to code this thing. Three, two, one. Stop share. So one more word about what we're once again we're trying to find the maxima and the minima of whatever like series of peaks and valleys we have. Let me share my notes. Okay, y'all can see this. Okay, optimization at 51:29 on B courses. Final project guidelines are on Piazza. If you're wondering like when this stuff is due, the 14th, I believe that's Monday of finals week, is when like the report and the MATLAB files are due. So I'll write December 14th, MATLAB files report are due. And then December 17th, those are when the presentations are going to take place. All right. I'm not sure if okay. So here's how we code this, kind of like the pseudocode version of what you guys will be doing. We're going to start with X naught. Here's our hiker. We're going to assume ascent. Okay, assign the position. This is our X naught. Assign the initial position to the current position. Let's say like X sub n is equal to X naught. All this is step one. We're going to initialize. We're going to loop over this. Now, you got to pick gradient ascent, gradient descent. I mean, you pick. Do you want a peak? Do you want a valley? Assign that to the current. You want to get the next position. So like xn plus 1 equals yada, yada. You apply the algorithm. So that's your new current point. Xn plus 1. And then you want to, so this part's the big part, but you want to repeat this until you get to the peak, until your hiker is standing happily on top of this peak and you can see your house from here. Loop until peak. Okay, one more thing, by the way. You might not exactly reach the peak just because of like how fast you're like approaching it, depending on your learning rate or whatever. You might like overshoot a little bit and then you'll go back and you'll go back. You might have like this sort of motion. I'm not sure that you'll need to do this, but like if you can't get exactly there, get almost there, by which I mean try like some sort of tolerance, like plus or minus some tolerance. It can be like pretty small, but you might not actually get there in some cases. And sometimes you'll just need to say, hey, we did the best we could. We're basically at the top of the mountain. We don't need to be like pinpoint precise. And then maybe break after X number of iterations. So like, let's say, oh, we've been running until the sun comes down. So like, let's say like, I don't know, 100 iterations. Break, something like that. They also want you to classify the extrema. So that's like the second derivative rule. I didn't cover that earlier, but I mean, this is something you'll want to do. Second derivative rule. I think it's like, so it's the determinant of what we call the Hessian. So, so you'll have something like this in optimization where you have partial of what is it? Partial of x, I think, squared. Partial of x, partial of y. I might be getting the orders of these mixed up, but I think it doesn't matter for this case. Partial of y, partial of x, and then partial of y squared. Am I getting this right? Let me check. Hold on. Okay, yeah, that's right. So you'll want to do this if the second derivative rule states this. If the determinant of this is like greater than or less than 0 or like equal to 0, you apply some judgment. I think let's check the PDF on that. So it'll say that like if the determinant is greater than 0, it's a minimum. That means that you have, actually, what am I sharing right now? Okay. So you have a minimum being, so I'm just trying to find like a place to write this. I'll like write it over here. Nah, not enough space. Okay, I'll write it really small. Determinant of h is greater than 0, then you have a minimum. That is a valley. If it's greater than 0, less than 0, then it's going to be like this. It's kind of like a curvature to my understanding. So it's kind of like, if it's less than 0, it's like the partial is, it's like it's downward sloping. That's what it's saying. If you move in the x direction, it's going to slope downwards. So that means it's a peak. So that's the second derivative rule. Now here's the whole thing, right? The 1, 2, and 3 only give you one extremum. One initial point and one strategy only gives you one extremum. There's two things that we need to do to get like different extrema. We want to pick a different initial position. Like, well, let's say this. We have this peak here, but we also have like a valley over here. Like, I'll like try and make this as 3D as I can. Okay, I'm gonna try like shading it a little bit. Okay, sun's over here. And then here's a valley. So we want to, if a couple things we could do. We could apply gradient descent, which means we're not going to go up the mountain. We're going to go like down this way. So that's one method. So use gradient descent instead of gradient ascent. So that's going to give us a valley instead of a peak. Initial position. This is if we have like multiple peaks. Let's say we have another one over here. And we want to, okay, well, if we apply gradient ascent, we're just going to go to the top of this peak. And that's the closest peak. We're lazy. We don't want to. So, but if we start our hiker over here, we're going to be able to like, oh, well, the closest one is going to be over here. So we're going to go to the top of this peak. Okay, now I'm standing over here. I can shout to this hiker over here and say, hey, what are you doing over here? So this is hiker number 1, hiker number 2. Different initial positions, different peaks. Different method, gradient ascent versus gradient descent. They're going to give you, say, a valley instead of a peak. That's the idea. Okay. Is Nikolai around? I'm just wondering. Or is he in a breakout room? Okay, I wanted to see if I said anything wrong so far. All right, I'm gonna go over, get rid of this in like 10 seconds. So screenshot this now.
Do we pick random initial positions? Or
wait, say it again. Sorry, my sound's a little low.
Yeah, do we have to pick random initial positions for gradient ascent and descent? How do we decide where we start?
Right. Fortunately for you guys, you'll be working with, and I'll show a visual of this later. You will know where your peaks and valleys are. So it's the peaks function in MATLAB. So I'll show you what that looks like. So you will know in advance like what this thing visually looks like. So if you don't want to like just brute force and like just pick a bunch of initial points that are within the function domain, then just like pick smart ones. You technically only need to pick, there's like 3 peaks and 3 values. So you really only need to pick 6 initial points, but you need to be smart about them. So yeah, if you know what's a good initial guess, then yeah, go for it. I'll show you guys what that looks like in a moment. I'm gonna Stop sharing in 3, 2, 1. Now, I promised you guys I'd show you the visual for this. Share screen. Nope, nope, nope. Yes. Okay. Let's start with this one first of all. Here's the second derivative rule I told you about. If it's, here's a minimum, here's a maximum, decide on that. Now, where's the visual I was talking about? No, not that one. I think it's after this one. Okay, here it is. Here's the peaks function. You should be able to visualize this with like mesh grid or something like that, but okay, let me just look up what this thing's called. So MATLAB peaks. Oh, like I think you should be able to, I'll find that later. But yeah, this is what it looks like. And there's 3 peaks, and then I think there's a small valley over here, like behind this 3rd peak. And here's a contour plot of what that looks like. So what I was saying earlier is if you pick a smart initial point, let's say like you start over here, another one over here, another one over here, and then apply gradient ascent, then you'll be able to pretty reliably with just 6 initial guesses get those 3 extrema, those 3 maxima. Same for the valleys. Let me see if there's anything else I missed. So the learning rate, yeah, okay, the learning rate. So make sure you just don't overshoot. I mean, it's this thing over here. I think you guys have seen this graph in lecture before. The advice is this: you want to pick something that's fast enough but doesn't overshoot, right? If you're like, remember the hiker, you start at, I mean, let's say this is our hiker, this yellow dot over here. Let's say we're like, our learning rate's really, really high, which means like we're running really, really fast and we're like overshooting. We're like running down the valley. Oh, I reached the peak and I overshot. Run back down, run back down, run back down, run down, and then you never reach the bottom. So you want to pick it so that it's not too discretized. So use a little bit of trial and error with that. Okay. Okay, both of these should be in B courses, by the way. The PDF I showed and then the slides for this. Okay. And so just as a recap, I can't answer any like conceptual questions. No, I can't do any debugging, but I can answer conceptual questions regarding what you're supposed to do here. And you'll have your groups for this as well, so you won't be totally in the dark by yourselves. All right. We knocked that out in pretty, okay. Any questions so far?
I have a couple. One real quick about the slide that you just showed with the mesh grid on it.
Yes. Let me pull it up again.
Yeah. Why is it not dumping into the? Wait, can you go back to the one with the arrow? That was just like it was just like a kind of an example of, yeah.
Oh yeah.
Yeah. Why doesn't it go to the local minimum? That's like it looks like it goes over the saddle and then back down.
I think that's just a very badly drawn arrow.
Oh, okay.
Yeah, I think it would just go here.
Okay, and then also the bonus point is choosing the right step size, or is it writing a function that will choose the step size as it goes?
No, you wait, the bonus points?
Yeah, I don't know. In lecture, he had mentioned that he like thought up a bonus point, sort of. Like he put it into the slides that we were. I don't know, it was kind of confusing how he talked about it.
Well, so the GSIs picked the bonus point. I mean, like that's subjective, but maybe he. So yeah, I think if the idea behind the bonus point is that like the GSIs can reward people who like go above and beyond. I think the idea there is make it, if you can make it more robust and like it'll handle more cases, like if it doesn't just work to the peaks function or something like that. But I mean, that's just a bonus point. I mean, everyone gets an A on this assignment, or at least an A minus. So if you're willing to put in the time and like do more than what the question asks and make it like, for example, if this could work for like another, like just a general function, not just like the peaks one, like if you can, because the advice for this one is you already know the function, you already know what a peaks thing looks like, but like let's say, would your function work for something with a different structure? Let's say the same domain, -3 to 3, but it had like a different number, like different location peaks and valleys. Would you be able to do that? Stuff like that.
Okay.
So I guess that could be, but like,
yeah, so it's not any like single thing that you
no,
guys
I asked for a rubric, and then Professor Lee responded with, let's just curve it. So the best ones get like a A plus some bonus points, and then the worst ones get an A minus. So,
Okay. Sounds good.
but everyone does well, so do not stress over this.
How would you propose like the best way to split this up is? Do you have like any advice for that?
For what to do what?
Like we have, what is it, 4 or 5,
Oh, you split the work, you mean?
5 kids in a group.
Yeah, good question.
Because like it seems, to be honest, like a relatively simple function.
Yeah. One thing you could do is this. If you want everyone to get the benefit of this project, try coding it yourself, like treat it as an individual thing, then come together with your ideas and how to approach it. Then, because you're going to come up with different ways of doing it, and you can just select the best one. That's one way. Or you can like just show up at your group and talk about it, and then yeah, I mean you're right. It's hard to divvy it up into different tasks, but you try that. Code it yourself, tackle it. If you have problems, go to your group and then like compare answers. Like yeah, do that. You do it as like a answer comparing exercise. But if you can like divvy it up, then yeah, by all means do so. I'm not gonna police how you guys split up the work, but ideally, like all of you guys do some work.
Dennis, for the presentation like aspect, should we have like a slideshow or something? Or like
Sure.
a presentation?
I think it won't be too strict regarding formatting, but yeah, something basic. It's just some way to show, or even if you just want to show the report. I mean, the idea is you go over your thought process, the formulation, how you formulated the problem, and yeah, it's possible I might ask like 1 or 2 like just very simple questions just out of curiosity, like how you did this, how you did that. Yeah, I won't like automatically make you like take off points for like if you don't have a PowerPoint. If you can summarize what you've done and go over that with me and Nikolai, you just going through the report, going through the code, that I'm satisfied with that. The idea isn't to create something too stressful.
Sorry, Dennis, can you guide us or like at least give us an idea of how to get the symbolic math toolbox?
Oh, that part. Symbolic, I think you just download it through, like when you download MATLAB, there is a way to do it. I'm not sure how you do it after you install. Let me check that. Symbolic, I think it's just a download, like symbolic math toolbox. I'm pretty sure just go on like mathworks.com and then download it from there. I haven't tried it myself, so I can't say for myself.
Okay.
Yeah,
do you think we would have had like already had it on our like in our download that we did? Or is it something that we would have had to click or whatever extra?
It's extras. You like
Okay.
select another checkbox.
Yeah.
So
Alright.
it's yeah. If you don't want to do that, they said Wolfram Alpha is okay if you are confident in your ability to type it in correctly.
I had a quick question.
Sure.
So what do we do if we're in like the presentation's gonna be during lab, right?
During lab, that's going to be December 17th, 3 to 6.
All right. So if we're in like a really bad time zone, like I have a 16-hour time difference.
Right.
So
So it's 3 to 6. If I remember, so 6 o'clock, 16-hour difference. So you add 16 hours. So let's see. So 16 minus 12 is 4. So it's going to be 10. If we let's say it's like 5 o'clock. Would you be able to do 5 o'clock? Because 5 o'clock is going to be 9 o'clock in the morning where you are, if I'm correct. Wait, okay. So is it plus 16 or minus 6? Yes, it plus 16,
plus
right?
16.
Okay.
Plus 16, yeah.
Yeah, that should be 9 o'clock where you are. If let's say we had your group go at 5 o'clock.
Okay, so I have actually changed my schedule, so I'm up all night and then I sleep.
I see. Okay.
I sleep at like 6 a.m. or 7 a.m.
So
Which
would
is like-
would no time in 3 to 6 work for you?
I mean, if there is no other option, then I'll make it work. But like I was just seeing if there is another option.
We could schedule a time that's outside the time slot, but preferably before, so that we don't give you an unfair advantage. I mean, it's pretty easy, I feel, but I mean, like, just to be fair. But that would need to be, you consult with their group and then make sure they're okay with that other time, because it's kind of like all the people need to show up at the same time. But we could do like an individual thing as a last resort, but ideally do it as a group.
All right. Okay. Yeah. All right.
Yeah.
Thanks.
So if there's any modification to that, let Amir or Nikolai know as soon as possible so we can make the necessary arrangements, because yeah, there are other people that are affected by that as well in your group.
Yeah. All right. For sure. Thank you.
Dennis, do you know if there's any way in MATLAB that we can like work on a shared file, or is it something that we'd have to send back and forth to each other?
Right. Yeah, I'm not sure about MATLAB. I know MATLAB is technically like all of them are just text files. So I'm sure if you have some like shared text editor, I'm not sure how tedious it would be to do in Google Docs if you can copy that over, because like sometimes it messes up the formatting. That's kind of why I advise like just doing it yourself and then comparing answers afterward and seeing like what works best. I don't know of a text editor that like is MATLAB that I know is MATLAB compatible and you can work off of it at the same time. Maybe like a Google Docs or something like that. But Rivik posted CodeShare.io. Okay, don't know about that, whether that works, but I'll trust Rivik. Looks interesting. Yeah, share that if it works. I mean, try that if it works. Well, try to see if it works, I should say. Let me stop sharing. Are people fine with me stopping the recording, or should we? Is there anything else we need to go over regarding? Let's see. Lab 12 is still going on, and the final project is live. I'll stop the recording.